with this distorted blackboard. I guess there's no one join the class, and then we just start. Okay, so we will talk about the last time we talk about the content error correction code, and then we basically showing there exists a qubit system that we want to encode k qubit, right, where the error can be corrected. And then we can define the code space of this k qubit such that they satisfy the criterion this is the state belongs to the code space C, right? And this is emission matrix. So that is what we discussed before. And then now we want to discuss more about the quantum error correction code. And then basically we'll try to introduce the stabilizer code kind of a concept. Okay, so let me just, this is a very brief kind of review. We did a lot of discussion in the previous lecture, and then I want to make some remark that we can show this quantum error correction code. The code state is highly entangled. So, as you know, because we need to make a k qubit state from an n qubit, meaning that we somehow have a more constrained conditions of this k qubit, embedded k qubit in a larger Hilbert space. So as you know, if I can imagine this n qubit is physically labeled in a position, then I can ask about the entanglement because I can do bipartition. And then since I'm trying to embed k qubits inside this n qubit system, then I must know how I correct the error. And then an error only happens in the local qubits, right? So if I only can access the local information, then that indicates this is not highly entangled. So I must have a way to correct the local errors for any errors in any position. Then conceptually, this state must be highly entangled. So now we just want to demonstrate one example. So let's consider so-called non-degenerate quantum error correction code. So when I say non-degenerate, meaning I have a more strong constraint on this criterion. The constraint I'm consider here will be this one. Replacing this emission with identity matrix, basically. Okay, so let me suppose this non-degenerate quantum error correction code has distance t equals to t plus 1. Then I want to show you this corresponding state is highly entangled. So meaning if I take a state which is a k-qubit state belongs to the code space, then I can perform a partial trace, and then now I have a error t, and then if you remember what the definition of error is the identity, the number of non-identity polymetrics for a polystring, right? So in that spirit, I can define a partial trace with respect to the number of t. So I'm consider I only split bipartite system into t and the t bar. So I can imagine I have a qubit for this space. I can this system can subject to error with weight t, meaning I can have number t of the maximum number t of vanishing poly operators characterize my error, right? So I can consider, suppose I'm bipartite my system, which this is t and this is t bar, which is the most possible support that I can have the error inside. Right? This is A and B. So I can define my reduced density matrix A by taking partial trace of B of this side bar, and this size belongs to this code space. And then I will demonstrate to you that this reduced density matrix will equivalent to this form, which is the identity, is proportional to identity. And as you know, if a reduced density matrix is proportional to identity, then this will give you the maximal entanglement. Maximal. So we want to show this. So how do we show this? So first of all, we consider this lead to a condition that I can consider this is the weight of arrows, total weight of t, and this can be reduced to this form for OA. For OA. Okay, so this is basically the setup we have. Okay, so with this setup, then that indicates this. I can take I bar equals to j bar, so it's equivalent to taking trace of row, because this row is composed by the superposition of I and j, and I'm taking the trace of this one, right? Subject to this evaluate because this EA must be 0 because this overlap is 0. Okay. I have this condition. Okay, so this is the condition I have. This one. So with this condition, then I can expand. We don't know the form of row A. Suppose the row A has a form that is the identity plus some superposition of all the possible polymatrices or the errors with weights t. Right. So this is the errors with weights t. So it will be the same like a dimension of the row A. Right. So we can do this kind of superposition. We just need to prove this alpha A is all the alpha A is 0. So how should we prove it? Basically, as we know, the quantum error correction criterion showing this one. Here. And as we know that we can rotated C corresponds to rotated code space. So let's denote the rotated as a tilde basis. And then after the rotation, this will be a diagonal matrix. So I just rewrite this as a diagonal matrix. This is after rotation, this is a diagonal matrix. This is the rotated basis. And then, as you know, taking the trace is independent of what kind of a basis you choose. So I can just directly compute the trace of this thing, right? So I can basically, I want to compute trace of EAEB, right? I'm just taking the same component, so this will be 1, and then how many I have? I have a 2 power t, so I can take trace of this one. Okay. Now, since I'm assuming this has this form, right? So I'm plugging this into my trace, rho A, EA. So the first term will be nothing, giving me this one, right? And then the second term is this and E, right? This is the second term. Okay. But as we know, by this non-degenerate code condition, this is 0. Okay. So what that indicates is this term must be 0 for all alpha, right? So this means, so if you know this times EA, I have an alpha A times this one, right? So that indicates I have a DA alpha B, or D alpha A, because I have a delta AB for this trace, must be 0 for all A. So that indicates even though the D is not 0, but I must choose alpha becomes 0. So if alpha is 0, then I prove this one. And this is mixed node. This is just a demonstration, demonstrated by an example that the quantum error correction code, the code state is highly entangled. But that is what you can expect. Now we want to talk to a more specific code called stabilizer code, and then we will try to give a more deep review of it. So as we show or talk in the previous lecture, for example, this majority code, the short code, what we can understand is, for example, like the short code. We have 9 qubits, but we only encode 1 logical qubit. Right? This is the physical qubit. So it seems that you need to take a lot of effort to find a constraint that lets you can do error syndrome detection, and you can correct error. And then it's just a question about if I want to find a large amount of logical, I want to construct a large logical qubit, for example, 2 qubits, 3 qubits, etc. Sorry, or multiple qubits from a physical qubit, then you can imagine it takes a lot of efforts to design, and then you need to search a very large Hilbert space, right? This Hilbert space is 2 to the power n, right? The Hilbert space dimension is too large, so it's not easy to find a way to brute force to several constraints to design a logical qubit, or design several logical qubits. So there should be a better way or a systematic way. It's called the stabilizer state. Okay. So the idea is there is a way to construct logical qubit by some formalism and by stabilize. It's called a stabilizer formalism. And this logical qubit or logical state is called the stabilizer state. This is the motivation, and then we just first trying to demonstrate some example and then get some feeling of this stabilizer code. So we just use our familiar source code. As you know, you can use source code as an example. So as you know, source code we basically have the 0 corresponds to some normalization. So 9 qubit. Right. 3. Source code. This is what we know. So the stabilizer formalism is trying to find some operation that basically act on this state. Okay. So what kind of operation? For example, we can find an operation. So let's denote, for example, Z1, Z2, Z2, which is the operation. And then we see this is basically I have 9 qubits. I only act Z on the first 2 qubits. So we can act on the 0 qubit state. And then the first 2 give you +1 plus 1. This is -1 plus -1, +1 plus 1, -1 times -1. So it doesn't change anything. Yes, right. So that indicates if I can construct a qubit state from this code space, then this Z1, Z2 acts on this is invariant. Right? Basically, give you the +1 eigenvalue. So now you just want to find sub-operators that act on the code state, give you the +1, which is the eigen, which is its eigen. The code state is its eigenvector with +1 eigenvalue. Okay, so we basically can find the corresponding Z1, Z2, Z2, Z3, Z4, Z4, Z5, and Z5, Z6, and then Z7, Z8, Z8, Z9, and then there's a X1, X2, X3, X4, X5, X6, and then X4, X5, X6, X7, X8, X9. Basically find 1, 2, 3, 4, 5, 6, 7, 8. 8 kind of operators that we denote this is G1 up to G8. Okay, and you can find that Gi at this code state if you +1 eigenvalue is the corresponding. So now you see there's some structure. So we code this is the stabilizer. This Gi the stabilizer. That stabilize the code space. This is eigenvalue. Okay, so with this kind of a structure that we can observe in the source code, and we can give you some kind of more structure of this stabilizer code formalism. So we can see there's 8 stabilizer for source code first of all. Okay, and then we can denote this stabilizer as the generator of some group. So we can denote there's a group with generator G1 up to G8, right? So we can ask about what is the order of this group. As you know, you can multiply all the generator to get a new generators or new group element, and then the order is the number of the group element, right? So as you know, this will equivalent to 2 because 2 to the power 8 order of group. Because you can consider you can generate arbitrary group from doing this product, which gives you 2 to the power 8 different kind of elements from this product. The number of elements of the group. Now, as we demonstrate this stabilizer or this source code stabilize the code, meaning give you the +1 eigenvalue, and then the code state corresponds to the eigenvectors of this stabilizer. Then we can construct the projector of the code space from the stabilizer. So this is why it's powerful. You can construct a projector of the code space from the stabilizers. So that is the reason why it's so powerful, because you don't need to know the state, you just need to know the stabilizer. And you can show in this example, the projector of the code space is nothing but this one. So I first claim this projector of the code space can be constructed from the stabilizer, meaning that I can show this is equivalent to just show this, and this is very general. So I just use this as an example. Just need to show this one. Okay. So first of all, in this example, we need to show this is a projector. So P squared must equals to P. So let's just first show this is equal to P. So P squared will be this one, right? This 1 plus GI squared, right? And then you can show that 1 plus GI squared is nothing but 1 plus 2GI plus GI squared. But all the GI squared is 1. So it will be 2, 1 plus GI. And then how many GI I have? I have 8 GI. So I cancel this 16. So it will be right. So it's back to the projector. And then next I want to show this projector as this form. Right. So what I can show is I just need to show is X on this. You can show easily because you know how this acts on. So you can first show all this acts on 0 or 1. If you 2s 2. So when you product is 2, you get additional 2 to the power 8, and there together with 2 to the power 16. So you will get this one. Let's show it. So from this example, what we can see is if the stabilizer code has what we observe from the short code, the shortest code, is that if the number of generator is a minus k for n-qubit system, and code space, the dimension of code space is k. We have, in this example, n is 9, we have 9 qubits, we have 8 generators, k generators, and this will be minus k. Okay. So we have 9 qubit system, k generators only in that 1 qubit. So this shows. We will prove this. Now, why this is good? Because this, although we are in the information class, but as you know that these states are very useful because as we demonstrate that quantum error correction code, the code state is highly entangled. Entangled states can be a very useful resources for doing quantum manipulations, right? For quantum, for example, quantum teleportation, etc. So this kind of stabilizer formalism provides a way that you can engineer or find the state from the Hamiltonian formalism. So, advantage. You can construct the Hamiltonian GI is the corresponding stabilizer, the generators, the stabilizers, for example, then the ground state, because the ground state will correspond to the lowest energy, and then the code state will correspond to the positive eigenvalue of GI, so which give you the most negative energy. So we can use this Hamiltonian to find the ground state, and the ground state will be the desired code space. Ground state. Code state. So this is some advantage. Okay, and then we can also design the control gate for this logical qubits. So we can design one advantage and design logical gate. So for example, we have 0 and 1 consider and then we can ask about how it acts on this one. And then, as you know, this do the flip 0 to 1, 1 to 0. So it will flip the plus to minus, minus to plus, right? And as you know, this 0 will be is the 0 plus 1. So it will still be the 0 plus 1. But the 1 is the 0 minus 1. Now, under this flip will be 1 minus 0. So we'll give you additional minus sign. So you can see this operator acts on this 0 and 1 will behave like a Z gate, Z gate, right? You know this is a Z gate act on this one. So we can also find the corresponding logical gate, which is the bit flip operation. So this is the base flip operation, right? And the corresponding one will be the Z act on one of the qubits in the 3 cluster, right? So we can also find, for example, the Z1, Z4, Z7, this kind of operation. For example, it is act on 0, it becomes 1, it becomes 1, it becomes 0, because it's only acts on one of the qubits in the cluster, so it's basically flip the sign. Okay, so you can imagine I can identify this as a control X, sorry, the logic X gate, right? Act on this logic qubit. And then this is very simple. You can also show this. It's just like a Pauling matrix algebra. This is a way that you can do. And then for this example, I can also ask about, since I have this kind of structure. So in the source code, if I can add one more generator, then the code dimension will be 0. That will be 1 because it's a 2 to the power 0, right? So I only have one statement. So we can also see this kind of a condition also hold. So can reduce code state by adding one more generator or stabilizer. So for example, the original generator is G1, G8. Let me add one more, which is the product of this Xi. Right. So now I have 9 generators based on this formula. The dimension. So in this, if I am applying this observation, then that means only left with one code state. So that's indicated as a 0 qubit. It's one state remain, and then you can show based on the stabilizer formalism. I can construct the projectors, right? So I'm claiming the remaining state. I'm reducing this is the remaining one. Will be the product of show this one easily. So with this kind of a demonstration, then we can also asked about does this content stabilizer code satisfy the content error correction criterion? Right, so we can ask about the correction criterion. So we just need to show that the criterion is we already written several times. So I'm going to show that is equals to CIJP. Right? So we just want to know, does this satisfy the content error correction code criterion for this stabilizer code? So now for this source code example, or for the example that we are interested in, the error is just a single qubit error. So we denote this error has three different types, which can be X1Z Pauli matrices, and then happen at location K qubits, right? So we can think this can be something like I also put the identity back. I don't do that, but let me do this. So, so this is just one single qubit act on some K qubit error, and let's suppose so we can consider different condition, right? So two possibility. We can consider two possibility. Because this is only Pauli matrices, I'm doing flip. Okay, so I just need to care about the commutational or anti-commutation relationship, right? So the first is this EI dagger EJ only anti-commute at least. So it can anti-commutes more than one, but at least one stabilizer GI. Suppose this is one possibility. Because as we know, this is composed by the Pauli matrix, and this is constructed by the Pauli matrix as well. So they either commute or anti-commute, right? So let's suppose this only at least commute one of the GI, at least commute more than one. Then we can do the following thing. So we just apply this one, right? This P is the product of one. So we can directly do this. So since I consider it's anti-commute at least one, right? So I can try to move this in the front, anti-commute with at least one of the GI. I denote it is a PTO type. Right. So what is the typical form for the PTO type? If I have anti-commute, then the sign in front of GI will change the sign basically, right? So with this kind of condition, we know PTO possess the form. Suppose I only consider one GI, then for this short code algorithm, I will put to the power 8, 1 minus the corresponding GI, right? The product of the J, that's equal to I, and then the remaining one is the same. Right? This is the form that we can have. Commute at least one, consider one, but 2 is also the same. Play around. Okay. Then you realize these two projector. So you can think this is another projector as well. But these two It's a very interesting structure because you have this kind of product. And as you know, this will give you 1 plus gi minus gi plus gi and then minus gi squared. Gi squared is equals to 1. Let's give you 0. So the right hand side will automatically give you 0. And if it's 0, then it satisfies this one because CIG is, I can just set CIG is 0. Okay. So the other possibility is they commute with GI, right? The second possibility is this commute with all GI. Right. And this will be simple because commutes I just move back. So this I can move everything around. So left with J E squared is equal to P. I just need to claim this is nothing but CIJ. Then proof is satisfied. Okay. So in this example, it's not hard to show because if they commute with PI, then we can just show that by example. If they commute with, for example, if EI is Pauli matrix X1, E2 is Pauli matrix X2, then that's basically E1 dagger E2 will be one of the stabilizer G1. And G1 again this gives you the +1 value. So it's basically showing that Cij will be 1. And you can basically show for its result. Because this can be composed of some kind of a product of the stabilizer. And if this can be composed as the product of the stabilizer, then it will give you the +1 eigenvalue. So this is a very generic setup. And then we want to show more because last time we already discussed the short scope algorithm, right? The short scope. Then we just want to discuss more about the short scope. And then, as we know, short scope cannot correct the error with weight 2. Right? So we can also show in here that it cannot be correctable because it violates the online error correction code criteria. So let's consider 2 error. Okay, so I can consider the total error and be including the original 1 error and then the other 2 error, and I indicate by alpha, sigma alpha I and sigma beta j. So ij is the physical location of the qubits, alpha and beta is x, y, z. So then based on what we discussed, right, using this commutation and anti-commutation to show that the criterion is satisfied or not, we can also play around with this one. So first of all, also 2 possibility, at least one anti-commute with G. 1. GI. And we also it will give you the same result. But the other one will be violated because the other one is they all commute. So I can find the example. So if they all commute, then that indicates I have this criterion. So So if this equality code then it indicates this system can correct two error, but as we know this cannot, and we will show this cannot. This equality does not hold because I can consider this error is just one error, Z1. This is composed of two errors, Z4, Z7, and then you realize what we are demonstrating, just like the logical X gate is described before, then this will not hold because this is not hold. So it's the demonstration that can correct two errors. So with this in mind, then we can discuss the more general setup of the stabilizer. Let's go back to the more general setup of the stabilizer mechanism. So let's suppose I have an qubit for this tree. Okay, so denotes by O1 times ON and then OK. Basically is 1 X Y or okay. So it's a polystring. Okay, so this polystring form a group. So this polystring let me denote that GP, which is a group. So we just need to what we learned from the short code that the stabilizer is a subgroup of this polystring group. So what is the group of a stabilizer is that this group of stabilizer G is an abelian. Basically, that commutes with all the elements. Subgroup of G, but without will exclude the minus identity. Then we can define stabilizer code. And the stabilizer code is defined as following. State is stabilizer code is such that Gi at this state is for OGI belongs to G. The statement. So this is the stabilizer code. This is the stabilizer. This is the formal definition. Then, if there are n minus k generated, G, then the code space this is one minus a, 1 plus gi. This is the same as before. Then we can ask about some structures using this formalism, right? This is the code space PC. There are other space, there are other projectors. Right. This is the Hilbert space, for example, and this the entire Hilbert space, and this is some code space. But there are other different space that you can use the projector to project into different space place in the Hilbert space, right? So we can define this projector in a very general sense, assign a vector x. So x is a vector which will be x1, x minus k, and xi is either 0 or 1, right? So I can define the projector in the following way. Minus k, 1 plus so different vector, get different one of the sign of the GI or some of the sign of the GI. So you can construct how many projector construct 2 to the power n minus k projector. Because this has different kind of combinatorial weight. So it's total projectors. We can consider this corresponds to the 0, 0, 0, 0 kind of a vector. There's other vectors, but in total you have 2 to the power n minus k vector. Right? So you basically have several projectors. So you can basically consider this all projector different space in the field space, right? So what we have is the total Hilbert space is 2 to the power n. So I can consider some of projector will correspond to the identity, right? Some of all the states, right? So we know the identity is equivalent to sum over all projector, right? So this basically, this can be considered as some kind of block form. So the dimension of this is 2 to the power n times 2 to the power n. I want to ask about how large is this block, right? Now I have 2 to the power n minus k blocks, right? So you can consider equally this is 2 to the power n, 2 to the power n, and then this has this kind of block form. I have 2 to the power n minus k block. So each block must be 2 to the power n k to the power k large. Right. So one of the block is the code space. Right. So how large? What is the common dimension of this code space? So we can directly show the dimension of P, which is the code space, will be 2 to the power k, and that is exactly what we prove. We demonstrate for the source code. Okay. Now we also want to give you more information about the distance. This is a very general setup. And then we can also discuss about the distance of our stabilizer code. So the definition is the following. So as we defined before, that I can have a G, which is a group of a stabilizer, which has a minus K generator. Okay. And then that's lit to K qubits for the whole space. Okay. So the distance basically defined some kind of error, right? The distance is sum of the Pauli string is defined by some Pauli string, summed by a set of Pauli string denoted by H, and I want to exclude this Pauli string from the stabilizer. So this set of Pauli string will contain no stabilizers inside. Okay, and I want to construct this set of string with minimal weight. That denotes D, and this minimal weight D will be the definition of the distance. Okay, so I have not show you what is the edge, what is this set of the Pauli string, the Pauli string. The set of this Pauli string is basically elements belong to this Pauli string group, but I want all these elements commute with the element in the stabilizer group. This is the setup. And then the minimal weight of this EI is the definition of the distance of this stabilizer code. So we can use one example. Suppose I have two generators, like this one. Okay. So in this case, N is 4, K is 2. So I have two logical qubits. Two logical. Right. So by the stabilizer formalism, the core space can be constructed for this G1 and G2, and then it's basically showing nothing but this one. The corresponding core space. So it will be either 0, 0, 1, etc. Okay. So now you can find the corresponding E1 and E2, which commutes with this G1 and G2. Basically, is the Z2 D3, D3, D4. They all commute with H, and it's defined. And then the minimal weight is. Okay. So for this code, the distance will be 2. Okay, so you can discuss about for 2, 2 code. So this is the very quick discussion about the stabilizer code formalism, and then we will take a break. Let's be back at 3:50, and then we will talk about the CSS code, which is one of the stabilizer code, but we want it has a more structure. And the reason is it's basically developed from a classical code called classical linear code. So we will just try to first review the classical linear code and then see what's the structure for this linear code. And at the end, we will try to show this classical linear code is a way to design a stabilizer code called a CSS code. So let's take 25 minutes break. We'll be back at 3:50.
然后放不下去。
线上也有，
现在没有了。
现在只有我跟那个。
不大不行。 你这样做，然后你最后就 只有弄出来可以把它更薄的对对，他们可以把它变异。对啊，因为你知道我是多少。对吧？所以它这个应该好。不完整，但是会小。因为它一下比较高。好啊，八。然后有脆子，也有可能是是脆子要。好，那脆子里面的这个你要看。好的，对。那你脆子就把这个。所以你 I 一定要等对，才会左右两边会是一样。这个加起来等于100，就是它有把 I 这个。对啊，因为脆子对啊，脆子掉。跟外面比来。这边 另外，就跟他们那个做去。这个应该还不太但他的意思是说，我这个系统增加一个编号。OK，立马就出来。对吧？多不必。方式。因为我觉得整个因为整个做完了，再去加一个，加一个。本来是标准的。可以可以好，这个的话。这就是刚刚那项目，就是那个爱跟这个一样的，对，然后这边是你剩下来，对对对，这个应该可以，它是 BJ 的，而且也是另外有勾一笔，假设这个你上面有一个派的话，那个太小了。对，这录音是零零，这个底层，这个也是底层，因为你看 BJ 对不对？啊，这里，已经的东西可以，就是只要有任何 BJ 撞到你，就等于到大。对，这个是 BJ 因为它是从右边，很像你可以先加，你可以加右，是这样。或者你看这个边边加，哦。结果一直在用，不要都直接用那个地方，最后找到一个。 对吧？对，哪题？该用了哪题？大概用哪题？好，欢迎哪天说要求，我们再帮他对。然后这个都要把这个都它这里。是去假的。跟老师不必要的，都送在那里。他们的基因都老师这里这样的。说啊，跟这个不是直接成绩。啊，对啊，这个想看，我就是看，想看的话，你啊啊法的问题。他真的就是看。也是移民他的地方。里面应该要提。那这里是知道。对啊。在这里应该有。那这个都是推出来的，这个要要求。这它是有先搞好的，对吧？
Two more. let's back to the class. So we will introduce the CSS code, and then before going to that, we'll just talk about the classical code because this is the one of the motivation to construct the CSS code. So this is the link. Sure. Motivation. Construct. It's the classical. Classical. So we just spend maybe just half an hour on today's lecture talking about mainly the classical linear code. So yeah, it also gives you some more concrete idea why we need to define the distance, the weight, etc. So classical system would have a bit 0 or 1. We have a string of bit, strings of bit contain some message. Right? We call it a binary string. Strings. Okay. Let's suppose called n. So that indicates it contains 2 to the power n bits. So I'm confident of the code, meaning I want to encode some binary string from these 2 to the power n strings. I want to encode 2 to the power k strings from these 2 to the power n strings. So when we say this, meaning there's a constraint. Or strings. And it's called code words. This is very, yeah, it's the information kind of concept that you can design code. Yeah, content information just trying to promote the content system. So this is more like a predecessor's kind of definition. So with this kind of in mind, we can define this string basically can be considered a vector, but this vector is a very interesting vector space. Strings, it's binary strings. Strings. If the vector space called the Fn2, which is the binary vector space, and it satisfies this kind of binary algebra. So we can consider example, for example, n equals to 3, and then I consider 2 encoded string. Basically, B1 denoted by 100, B2 denoted by 101. I can do this addition, right? So 1 plus 1 is 0, 0 plus 0 is 0, plus 1 is 1. Same is all vectors in this F2 n space, F2 3 space basically. So this is some kind of structures. So with these structures, the code words, basically these 2K strings is the subspace of this F2N, right? So the 2K string is subspace of subspace of C of F n. So basically, I can have a k dimension vector space. And by the way, this is a n dimension vector space. So this will be k dimension vector space. So I can have k vectors denoted by B1 C. Okay, so I can construct a general code word from superposition of this B1 up to Bk, right? So it should be the code word. I can deliver the information can be expressed by this form. And of course, this coefficient is either 0 or 1. This also satisfies this control. Sure. So with this in mind, we can ask about what is the constraint to design to design or to encode this K string. I need to have a constraint of this B of K. So then it defines so-called generator matrix. Which is K row, right? And this 10. So 10 K times a matrix. So I want to have a constraint. This vector, and then I know the general vectors in this code. The subspace can be expressed in terms of this coefficient alpha. So I can basically say I can encode information in terms of alpha I. So k bits information can be encoded alpha I, right? Because alpha also forms a array. So I can consider this, give you a superposition of this one. I can consider this V, denoted by this alpha. Alpha can be considered as a vector. It considers this kind of product. So you can imagine this is the alpha 1, alpha k times this G. To give you an n. That's n. Okay. So I want to have a constraint of this V. Constraint V alpha by consider struct comparative check matrix. want the P times B is equal to 0. So P, so if it's this form, P, so P something like S1, this is N, this is K minus N, this is times array N, because from this time this is array N. Want this to be 0. Okay. So what does this mean? I have a k minus 1 vector, so this can be considered as a vector that's orthogonal to this V. That's the case. Yes. K minus 1 that's orthogonal to V. Right. So this is a constraint. I want to have a constraint of this V by a set of vector that's orthogonal to this V. That's the idea. This orthogonality is respect to the vector space F2. But this formalism, in other words, is all the V, they also this P also orthogonal to all the vectors in V. It translates this by the G transpose equals to 0 because G transpose is V1, V2, is right. Okay. So it's also satisfied this kind of form. So this is equivalent to have this condition. In this classical system, the only error that can happen is the bit flip error. So this is the only error we can reader. Because when we say the code, the error correcting code, it's classical meaning code, which can correct an error. The only error is the bit flip error. That's the reason we can define the distance, because we can define the weight of the error. How many bit flip can happen? Bit flip. So we can define the distance. So in the classical system, the Hamming distance. So we have the distance basically is comparing the distance between two vectors, right? So I can consider the distance of two vectors V1 and V2. Let's just demonstrate this by the example. So if this is 0, 1, 1, 0, 0, this is 0, 0, 1, 1, 1. So I've asked about how many bit flip that act on V1 can goes to V2. That's defined the distance. So I need to flip 3 bits to change V2 distance is 3. So this is the definition of this distance. We also can define the weight. Distance and the weight. The weight is the same definition as what we can imagine non-zero entry. Okay, so the weight for V1 will be 2, weight for V2 will be 3. Simple definition. So you realize for this binary string, then the distance and the weight can basically combine with each other. There's some relation because I want to compare the distance between V1 and V2. So the distance between V1 and V2 will be equivalent to the weight of V1 plus V2 because of this binary algebra. Because V1 times V2 will be basically counting how many difference between V1 and V2, right? So if you do this algebra, it will be 1, 0, 0, 1, 1, and the weight is 3, which corresponds to this 3. This 3 bits, location of this 3 bits that I need to flip going from one to the other. So this is the very good advantage. Find the weight, find the relation between the weight and the distance. Now the error, what we call about error. Error is the bit. So we can also define the weight of the error, basically how many flip that you can happen, right? So we can say there a T error, meaning I can have this bit flip on T bit, right? That indicate the error at V, for example, V, and the distance between the V plug and V V is T. That's what's a very simple definition. So now I want to ask about the correction of the error. Correction of errors. Also, which indicates that I can distinguish different errors. Okay. So with this definition, then I can define that this is the code distance. Let's do the example. So it's the same as before. So two whole words must have the distance equals to 2t plus 1 to distinguish errors. Wait. Because if the maximum possible of two error acts on the state, the maximum this distance is 2t. But I want to distinguish them, so I need to have more distance. That is the idea. So we can demonstrate from example. For example, I have these two whole words. Example, like this one, right? These two words, the distance is 4, right? Because these two, 4. Now, if I can subject to some error, I have two error denoted by E1 and E2, right? Let me denote the E1 is the bit flip on the last two, and the E2 the bit flip on the first then this subject to E1 will be 0, 0, 1, 0, 0. This subject to E2 will be 0, 0, 1, 0, 0, which this is the weight t equals to 2, kind of error. And you realize it cannot be distinguished. You cannot distinguish these two sides. So you don't know this subject to E1 or E2. So it cannot once you cannot distinguish it, it's not correctable. So that indicates your code words must have one larger distance than the case that you cannot distinguish. This is an example. So in this kind of setup, then we can define a classical code. Y and KB. Function version is just with double brackets. So with this definition, then we can try to use this use this kind of classical linear code formalism to see why we can correct code and how should we correct it. And so this, remind you, this is the setup of the classical linear code. I have a constraint of my code words. So let's suppose there's an error that act on the code words of this classical linear code. What will happen? Right. So let's suppose there's an error. I have a code word denoted by V. I have an error denoted by E. Right. So when this acts on the code word, I can just do this simply. So for example, if this is 0, 0, 1, 1, 0, and this is 0, 0, 0, 1, 0, and this indicates there's an error happened on the fourth bit. So this will be 0, 0, 1, 0, 1. Error happened. So I can use a vector in this F2N vector space to characterize the error. Now for this classical linear code, I have a constraint which the parity check X on V will be 0. So we can ask about if this is the corrupt one, then it will not be inside the code space. Then it will not be 0 and it becomes PE, right? So the idea is for different E, if PE is different, then I can distinguish the error. So if E1 is not equal to PE2, or E1 is equal to E2, then error are distinguishable. So if the error is distinguishable, I can correct the error because the corrupt code words is this one. I can correct it if I know the error is E1 by adding one more error back. So it's correct. So this is logic of this classical linear code. So this is some kind of error syndrome. So this is still a very simple idea. So if on the other hand, if this is equal or this is not equal, I cannot distinguish. It's easy. Okay, so this is the idea, and then you can show. I will let you more. So this is a very like a simple setup. Now we can consider a more general setup is, let's suppose the set of error epsilon contains all errors with weight t contains all error is weight at most t, because I want to connect it to the definition of this distance. So the distance of the code must be 2t plus 1. So the of a classical code is distance. So this is a statement that for an error that the weight is at most t, for a classical linear code with the distance 2t plus 1, then the error must be distinguishable. So this is okay. So the idea is you can prove by contradiction. For example, so suppose PE1 is equals to PE2, right? Then you can basically move this to the other side. To be 0. So that indicates E1 plus E2 must belongs to the code space. However, the E1 plus E2 with its weight T. However, the weight of E1 plus E2 is at most 2t. But the code space has a distance 2t plus 1, indicate the minimum weight is 2t plus 1. Contribute. So if E1 is not equal to E2, right? Because if E1 is equal to E2, this is equal. So that's basically proof that this is not equal for E1. So with this kind of it's a setup, then we can try to also discuss some structures of this linear code. We can also construct a dual code space. A dual code space. And we can also discuss about self-view. What that means is I can consider I have a code space. I can construct a dual code space for C perpendicular. Construct it from the following sense. So we have this kind of structure. C equals to 0. So I just do the transpose of this one. So so now you see what you can define is this is can be considered as parity check matrix. I define it as a code space. So, code space definition is particular code space. Okay, so this is the generator matrix of C. Okay, so it's a very easy way to construct by just taking the transpose. Okay, and as you know, this binary string, if I consider the even bit string, then there's a possible way to make it self-deal. So if the string is even length, then I can find self-deal. So which means C is equal to C. So we can just show by example. One is 0, 1, 1. B2 is 1, 1, 0, 0, which I said belongs to C, and you can play the same thing by taking the transfers. B1 perpendicular to 1, 1, 0, 0, B2 perpendicular to 0, 0, 1, 1, which belongs to C perpendicular. This is one example. Just better ones to formalism. Okay, and then for this kind of a dual space, we also have some property. Okay, so the condition. So the condition is the following. Let me denote the code word belongs to C, and I want to sum over all the code words. Then we denote this code word B. I want to sum over all the code words belongs to this C. Will be equals to 2 to the power k. If this U belongs to the C perpendicular 0 otherwise. This is the constraint for this dual space. So if U belongs to C perpendicular, then we know this must be orthogonal, right? So if that orthogonal, then meaning this inner product 0. So it will be plus 1. How many plus 1? 2k plus 1 to the power k plus 1. So we get the first thing. See? So the other thing is, if U is not belongs to the dual space, then meaning this is not 0, right? So if it's not 0, then this inner product will only give you 1. Because this is a binary system. You cannot get that. Just trying to say one more time. So if U belongs to C perpendicular B dot U must be 0. Sum over B belongs to the whole space and then minus 1 0. if U not belongs to C perpendicular, then B equals U must equals to 0 becomes 1. Okay, so that indicates that you can rewrite this U. So the condition is G times U. Remember that G will replace G is behave like a parity check for C perpendicular. So the condition is this is 0, no, this is not 0, right? And we just apply this in here. So it will be sum of the B belongs to C minus 1. That's V dot U. And then I need to replace V dot U by what is V? By definition, V dot U. But V can be considered as alpha times G, right? As we defined before, this can be considered. I just want to replace this V by sum over alpha. And alpha, all the alpha index is 0, 1. So I can replace this by alpha G dot U. But G dot U is not 0. So I just need to sum over alpha. So now I replace sum over V by sum over alpha. By sum over alpha. Alpha is 0, 1. This is not 0. So it will lead to plus minus 1 plus 1 with all the different alpha. So this is simple. Okay. So with this setup for classical code, classical linear code, and we can try to introduce the CSS code, but I will not talk today in detail. I just talk about one thing that's also related to classical linear code. But as you know, the difference between the classical code and the quantum code is quantum code had an additional error, which is the base error, right? So the classical code, as we discussed here, it corrects the bit flip error very well, right? So now you want to find a way to correct additional error, meaning you need to find more constraint. Right? So the idea is in more constraint. More constraint for the quantum code. That has the same structure. The same structure of classical linear code. So I just need to find a way to adapt this classical linear code with more constraint. How I do it? So let's suppose I have a classical linear code. The logic is the following. I suppose I have a classical linear code, and then let C1 is the code space. Classical linear code. With the parity check matrix. One is the following form. This is n. This is n minus k1. I want to find a subspace of this C1, which also characterized as a classical linear code. So the idea is I want to do the thing. I want to encode it another code space in this C1 code space. Then let me consider a C2 code space, which is the subspace So as you know, if it's a subspace of C1, that means there's more constraint on C2. If the C2 has more constraint, that's meaning the corresponding parity check matrix is larger. That's a small condition. Which look at the corresponding parity check matrix should have the following form. First entry, the first upper one is the P1 that has this structure, right? And this is the remaining one. This corresponding will be M minus K2, and this will be K1 minus K2. So K2 minus K1 minus K2. So K1 is greater than K2. So now I have a structure of C2. C2 has a larger parity check matrix, which corresponds to more constraints, so it has a smaller dimension, and it's embedded in this C1 space. Right? Now, I want to define the equivalence between two vectors in C1 and C2. That is the reason I want to construct a more constraint of a code space by setting some equivalence class or equivalence between two vectors. So we can define equivalence, and now we can define equivalence between V1 and the V2 is two code words belongs to C1 by C2. Okay, how we do that? By saying that if so the notation is V1 is equivalent to V2. Right? So this by C2 meaning if and only if there is belongs to C2 such that V1 plus U is equal to 1. So I'm basically reduce furthermore of my code space, because if these two are equivalent, they are the same. This new setup. So the equivalence, in other words, is trying to group the V1 and V2 together. So there's some kind of concept. So anyway, talk about this. So as a result for this construction, then the remaining thing of this, the remaining equivalence vector will be K1 minus K2. So equivalent vectors of both words will be 1 minus K2. So the design, the CSS code, will be denoted as N K1 minus K2. So that's basically is a pre-introduction about the CSS code, which we will discuss for the next lectures. This is for today. We discuss basically the stabilizer code formalism, the highly tangled from the structures of the content error correction code, and then we just want to jump to another code called the CSS code. But before that, we need to introduce the classical linear code, which demonstrates some structure of the classical linear code. Reminds you why we need to define the weights, the distance, etc., which characterize the code, and then using the same spirit as we discussed before, this classical linear code is very convenient for the error detections, right? And correct error is this criterion for the parity check. That is for the classical linear code. Next time we'll just use this and then adapt to the content code. That is the CSS code. So that is for today. And the class